Yeah, how much longer should we give it?
You can start now if you want.
Okay, yeah, there's three people, and so I just wasn't sure if we wanted to wait for more people or.
No, it's okay.
Okay,
I just pasted the let me see. We put the
yeah,
sheet, put on the command.
I believe I have the git clone command ready to go actually.
Okay, good. Okay,
Okay,
okay, go ahead.
and I will share the correct window. Okay, okay. Yeah, so my name's Irene. I believe you can see my assistant Daisy in the background. Um, this is going to be uh, an introduction to solving differential equations numerically on the university clusters. So to get started real quick, first things we're going to do is to access the materials using either the git clone command that is in the chat, or if you've already cloned that, you can just type git pull to get the new material. Um, so most of it is in Jupyter Notebooks. So to do that, we can just, in interactive sessions, just the Jupyter Notebook, we can use pretty much the default things, an environment module, the most recent Python, standby queue 4 hours, only need one core, it's a Jupyter Notebook. And then we will launch that. I feel like it usually goes quicker than this. Okay, and then we can connect to Jupyter. You will navigate to where we put those files, DiffyQ Workshop, and today will be background and computational fluid dynamics. Okay, so I'm going to assume very little background here. So, derivatives, when we're doing research, when we're considering some quantity like the distance we've traveled or the pressure or velocity of a fluid or electric and magnetic fields, um, quantum mechanical wave functions. Um, Something we find is that the quantity, how that quantity is changing is just as, if not more interesting than that value itself. So we'll often find ourselves trying to look at the instantaneous rate of change in that variable, which we call the derivative. And to get a derivative, we do what we call differentiation. Um, so a very common example that you'll see in day-to-day life would be the odometer and speedometer in a car. So the odometer will measure the total distance that the car has traveled, but moment to moment, we care a lot more about the car's speed on the speedometer. That's usually what will get you in trouble as opposed to just the distance. So by definition, speed is called the first derivative of distance. And then if we take the derivative of speed again, we get the second derivative, which we call acceleration. Another common way to think of derivatives is the slope of a curve at a point. So just to illustrate that real quick, if we're looking at just a basic parabola like we have here, the derivative of that will be the slope of this curve at some point. So the derivative here would be a negative quantity, and it'll go closer to zero and then start going positive and getting bigger. And then we can illustrate that here with a tangent line at this point. We can see that the slopes match perfectly here. So then, since we find derivatives with differentiation, a differential equation is just any equation that involves a variable as well as derivatives of that variable. So these equations have numerous important, diverse applications all over the place. You see it showing up in finance, in compound interest. It can show up in population growth equations in ecology. And then to focus more specifically on what I'll be talking about, the physical applications, we see them quantum mechanics, thermodynamics, electromagnetism, relativity, the heat equation. So in these sessions, we're going to be focusing on three sets in particular: the Navier-Stokes equations of thermodynamics and fluid dynamics. That will be day one. And then tomorrow we'll be talking about primarily Einstein's equations of general relativity, as well as Maxwell's equations of electromagnetism. And we'll also be looking at the intersections of those three sets of equations in something called general relativistic magnetohydrodynamics, as well as a special case of that that's a bit easier to work with, general relativistic force-free electrodynamics. And then I'll talk about these equations in cursory terms. We're not going to get too deep into the math behind them. We're going to be focusing more on the computational side of things. So as powerful as these equations are, we get very good predictions out of them when we look at things like the weather or merging black holes. They are also very, very complicated to solve. In fact, we can prove that general solutions to these equations, such as we might normally try to find in math classes, just don't exist. And in fact, the only exact closed form solutions that we have found to these equations are typically extremely limited in scope. Only like very simple cases that are unlikely to occur in the sort of things that we really care about to try and describe in the real world. So, an exact solution to fluid dynamics might be a perfectly sealed, completely still volume of air in perfect thermodynamic equilibrium. But the sort of thing that we're trying to describe for practical applications in the real world is the weather, which is a little bit more complicated than a sealed Tupperware container of air sitting in the freezer. So that leaves us with the resort of having to find approximate solutions to these equations instead. So how do we find these approximate solutions? So to do that, we are going to use computers. Uh, so typically, these equations are defined for the real numbers, sometimes the complex numbers, but the important thing is that the values are continuous. So a way to think about that is no matter how close two real numbers are, there is always going to be some other number in between them. Um, Unfortunately, computers cannot do that. To store an infinitely long list of numbers like that would require an infinitely large computer. If we were to wanted to try and do something like perfectly record the pressure in a volume of air at every single point within that volume. And this will apply to things over time as well. If we wanted to perfectly mimic time, that would require us to end up taking infinite time steps, which would mean we could wait until the heat death of the universe and we would be no closer to actually getting a solution than we were when we started. Um, so we're going to have to break down the system that we care about into much, much smaller pieces. So we're going to do something called quantizing our domain, and we're going to get little building blocks that will make up the system we care about. So in space, this will involve subdividing it into a grid of cells. The simplest case for this will be just a grid of cubes, all uniform in size, neatly stacked together. But that has its drawbacks. There are more fancy things, and we'll look a little bit at those as we get further into things. Um, and then we will record, we will, instead of thinking about the whole variation over that cell, we will just sample the quantities that we care about at some point within that little box. So oftentimes that'll look like, say, we measure the pressure at the center of the cube. And then, but sometimes it'll be like the face or the edge or the vertex of our box, depending on exactly what we're trying to do. Um, we'll also have to quantize things in time as well. So we'll call those, so we'll be taking small discrete steps of time forward in time that we call time steps. So that might be like, we'll compute from 1 second to the next, although a lot of the time we'll want to use a much smaller step than that to get accurate results. So to approximate a differential equation, we're going to, using a method that steps forward in time, we'll take some starting value at the beginning to program into our simulation. So a good example to look at here will be compound interests or bank accounts. So in that case, the initial condition would be the principal amount in a bank account that's getting interest. And then we will look at how that changes as we go to the next time step. So a bank might, instead of trying to solve the compound interest equation continuously, which it's a simple equation, is much more straightforward than some of the ones we'll be looking at. So you can do it. But what they typically will do is every, say, month or so, they will compute the interest. So they'll multiply the interest rate by the current balance and then add that amount of money to the account for the next month. And then when we're looking at more complicated simulations, like a computational fluid dynamics simulation for like a volume of air or water, we will then, that time step calculation will have to be done at each grid cell within our domain. So then, now that we have our computational domain, now that we have that quantized, we'll be ready to start simulating our system of choice. So I already mentioned initial conditions. Those are often usually governed by something that we call constraint equations. So when we have our system, be it fluid dynamics or general relativity, we'll have multiple differential equations that we have to look at that each govern different quantities. So we can sort these types of equations, or we can sort these equations into two types. We can call them constraint equations and evolution equations. The constraint equations will govern the behavior of the system in space at a single point in time. So we can use those to help calculate the initial conditions to make sure we're starting from a place that is physically consistent. And then we also have evolution equations. And those will be what we use to tell us how this system is going to change over time. And then another thing that we'll need to consider for our simulation are the boundaries of our computational domain. So as I mentioned before, with computers having limited capabilities, limited memory, limited computational cycles, our domain necessarily has to be finite in size in both space and time. So I already compared that to a Tupperware container of air, and that has boundaries. And then we're also going to be looking at that in a fixed interval in time. So we're going to have to define how our simulation interacts with those boundaries. So if we want to model airflow through a duct, which is something we'll be actually looking at in a little bit, the boundary condition might be intended to mimic the solid sides of the duct or the inlet of the duct or outlet. In astrophysical simulations, it'll be trying to approximate the infinite expanse of space beyond the computational domain. And if we don't do this properly, we can get weird unphysical results. Again, in astrophysical simulations, if we don't set our boundary conditions correctly, we can end up with gravitational waves emitted from an inspiraling black hole binary, reflecting off of the boundary of our domain, which represents empty space. And then those can get back to the black holes and affect their behavior and throw off the entire simulation. So in summary, our scheme to approximate a differential equation will look like this. We're going to first set up the initial data to using the constraint equations and whatever we know about the system we are trying to simulate. And that will be at some time that we'll just call time zero for convenience's sake. And then we will advance forward in time in discrete time steps. And at each time step, we will use the evolution equations to estimate just how much the variable should change over the course of that time step within each grid cell using the, and then we will add that change to the variable for the next time step. And then we'll apply boundary conditions near the edge of the domain to make sure that things are behaving nicely at the edges. Okay, so I'm going to stop sharing my screen for a moment. And we are going to pop this out for my convenience, put it over here. Okay. Also, I actually click that button. Okay, so the example that we're going to be doing now is laminar flow through a pipe. So laminar flow just means that the fluid is going to be flowing in uniform layers. So that this is what's going on when we see those rather pretty videos of like water flowing out of a tap, and it's so perfectly smooth that you can barely even tell that the water is actually moving. So we're going to be doing this with ANSYS Fluent, and we're going to be using on-demand, an interactive job to do this. So we're going to use the desktop with GPU. We're going to use these settings, just 4 hours, 4 cores, a GPU, ANSYS 2022, and we're going to launch that. And then once this launches, it's going to automatically launch the ANSYS program for us, and we will be presented with the workbench window. Okay, so I'm going to adjust this a bit. Okay. Okay, so we are now presented with the workbench. So over in this panel, we can see a lot of, we can see the various ANSYS simulation products. The one we want is Fluent. So we're just going to drag that over to the project schematic, and we're going to get a new project. And then the first thing we need to do is going to open up the geometry. This will start design modeler. So this chat. Thank you. So this is the built-in tools. This has basic tools for setting up the geometry that we're going to work with. But there are also options to import pre-made geometries from more robust programs like SolidWorks. Okay. So the first thing we're going to do is we're going to select the XY plane, so that we're drawing in the XY plane in 2 dimensions. And then we're going to sketch, and we're going to create a circle. And we're going to center it on the origin. Okay. And then we're going to assign a dimension to it. So a dimension that we're controlling, we're going to give it a diameter. And then that shows up over here. And we're going to set that to 0.2 meters. And then zoom back in. Okay. So And then since we're doing a pipe, we're going to just extrude that circle. So we're going to click on this tool, extrude up here, applying it to that circle. And we're going to set the depth or the length of our pipe to 3 meters. So we can see that now there. And we are going to click on generate. So now we have a nice 3D model of our pipe. So that is the geometry we need for this. And we will close out of that. Okay, next we will open the meshing tool. So the meshing, as this is another word for the quantization of our computational domain that I mentioned earlier, because mesh is much easier to say, it's only one syllable. Okay, so this will automatically bring up our pipe geometry for us as soon as it's done initializing everything. Okay. So we're going to add a method. So how are we going to try and do this? Select the geometry, which is the pipe that we're going to apply this to. And for the method, we're going to just use tetrahedron. So this is another option. This will since it's a simpler shape than cubes, this will allow it to better fit to the curves in the walls of our pipe. And then we can click on generate. So now that that's generated, we can click on mesh to see the mesh that we generated. So we can see now we have this grid of tetrahedrons that is fit to the pipe. Okay, and then going back to the selection tab and clicking faces. The next thing we're going to do is name the parts of this mesh. So by giving names to the boundaries of the mesh, ANSYS will be able to automatically detect the type of boundary that it is. So we can select this one here and then create named selection. So we'll call this the inlet to our pipe. Not work the way I was. There we go. Okay. And then we can call this the wall. And then we can call this other end the outlet. Okay. So that's the mesh, and then we will right click and update. And then once this is done, we'll be able to move on to setup and actually solving the system. Okay. So we'll double click on setup. And then we'll want to use double precision and then increase the solver processes. So this will be matching the cores that we set up earlier. So that's 4 in our case. And we'll start that up. Okay, and again, we can see that it's pulled up our pipe already. And we can also see by the arrows, it's already gone ahead and identified the inlet and outlet that we specified. Okay, so we're going to set the model that we want to use. So this is viscous fluid. And as I mentioned before, we're going to use laminar flow. And then we're going to set the material that we're using. So we can see that this does come with a library of predefined fluids, air, water, various other chemical things that one might care about. For our case here right now, we're just going to manually set the density and viscosity to make sure that we are in fact meeting the conditions for laminar flow. And we're going to save that and close out of this window. Now we need to refine our boundary conditions. So the inlet, we're going to give this a velocity. We're just going to set that to 1 meter per second. So this is mimicking the scenario where we are forcing air from some source at a fixed speed through the pipe. And then our outlet boundary condition is going to be at a set pressure. So we're going to set that to atmospheric pressure so that we're going from some fixed source that's giving us a constant velocity through our pipe out into the open air. So atmospheric pressure in pascals is that many. Okay, so we have the things I mentioned. We have initial conditions. We've defined the properties of what's in our system by like the material is a fluid. So now we're going to start looking at solving this. So we need to initialize it. We'll use standard initialization this time. We're going to compute from the inlet towards the outlet. And then we will click on initialize. And then we can set the number of iterations. So this will be how many steps it's going to take to refine the numbers in the system and make sure that we're not violating any important constraint equations laws. And we will just click calculate. And then we can see okay, I will talk about that on the longer calculation for the next example, I guess. So that's the calculation complete, and it's time to go try and look at our results. So we'll close out of this, and we will open the results window. And you can see it is starting up the next program. Okay, so we first want to create a location. So this is going to be, where are we looking at the results? Because it's a bit difficult to represent three-dimensional plots on a two-dimensional screen, especially when you're also looking at a color scale in there. So we're going to get a plane, and we're going to set this to the ZX or YZ plane. It's not going to make a particularly big difference in here. Apply. And we'll also click down here, view along the y-axis. So now we're looking at the pipe face on so we get the best view of it. Then we will create a contour plot. And then we're going to look, the location we want to look in is the plane we just created. And we're going to look at the velocity. Click on apply. And there we have the velocity through the pipe. So this is, as I mentioned before, laminar flow. And we can pretty clearly see the layers through here of different velocities traveling through the pipe. And it's faster in the center of the pipe because near the edges of the pipe, the air is going to be flowed down by its interaction with the walls of the pipe, dragging it, slowing it down. And then if we are so inclined, we can also look at the inlet looking along the z-axis. And so, right, at the inlet, we have a very constant velocity because we defined that to be a fixed velocity at the inlet. And then if we look at the outlet, we can see that it's traveling faster in the center and much slower near the edges of the pipe because of that interaction with the walls of the pipe as the air has traveled down it. Okay. So I will pause briefly here to check for if there's any questions. And then once we've done that, we'll take a quick break. So does anyone have anything?
A quick question, Irene.
Yeah.
So the imperfections that we see, for example, here in the plot that you showed,
Yeah.
let's say the polygons that you see, for example, in the center is not exactly a circle, is due to the geometry of the pipe, or
Yes.
the way
Or
you
the mesh.
segmented with the mesh? Is the mesh?
Yes. Yeah. So if we wanted to get things more smooth, we would need to increase the resolution of our mesh, but that has the effect of dramatically increasing the time to calculate.
Okay, so is the mesh that is creating those features, or those, it's not the geometry. The geometry is a perfect mathematical cylinder.
But no. So
No? Okay.
it is defined by the mesh.
Okay.
So
Okay.
it's quantized into those tetrahedrons.
Okay. Okay. And are those tetrahedrons the best choice for this? for this kind of geometry, for something that is a curve. Let's say a tetrahedron is like a pointy thing. This is like, uh,
Uh,
do,
right.
or
So,
there are other options for that. I don't know. I have no idea. So I
um,
question out of my ignorance.
yeah. So maybe not necessarily the best,
Mm,
um, but uh, with the tetrahedrons, we have more freedom with how we stack them together than we would with like cubes.
uh-huh.
So they are pointy, but we have the freedom to make sure that the face of the tetrahedron is as flush with the geometry of the ideal perfectly round pipe as possible. So as you asked about before with the geometry versus the mesh, what's causing those imperfections? The geometry is sort of more idealized, and then when we get to the mesh that we're actually working with, we're quantizing it into something a bit rougher.
Okay.
Um, but using tetrahedrons, we can try to make sure that a flat edge of the tetrahedron is always up as close as we can possibly get to that ideal perfectly round pipe.
Okay.
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 So I
And
think,
how you select, let's say, I don't know, if I see the blue polygon, let's say the cylinder, it's like they have like probably 40. It's a polygon like it's not an icos. It's not an icosagon, but maybe it has like 40 edges in the or
mhm.
faces. Is something that you control with the mesh creator in the list of steps. Is
uh,
something that allow you to make a smaller, finer tetrahedron. So let's say a much smaller, and that will make this to look better.
yes.
Oh,
So I left it to automatic for this example, but I
okay,
will, in the next example, I'll mess a little around a bit more with the
okay,
options there.
okay. Go ahead, go ahead.
But yeah, if you increase the resolution, decrease the size of the tetrahedrons, we'll get more edges as we get closer and closer to a circle.
Okay, good.
Okay, so I think I will pause until 250 here, and we will reconvene then. Okay, so I'm going to go ahead and get started again. Yeah, so yeah, the grid sizing. Yeah, as I was just mentioning, or sort of alluding to, getting the correct grid sizing is extremely important. Um, so beyond just a little bit of blockiness in your model, we also need to make sure that we're adequately sampling the space in order to resolve any interesting features of the physical system that we're trying to simulate. So for the laminar flow in the pipe, that was mostly just the change in velocity across the length of the pipe as well as the diameter of it. So the most important thing is that when we're trying to numerically estimate derivatives on a quantized grid like this, we're essentially sort of trying to guess at the actual shape of the underlying function from the nearby points. So if we don't sample this finely enough, we can get wildly wrong answers that don't line up with reality and completely break our simulation if we're really unlucky. Divide by 0, take the natural log of a negative number, all kinds of bad stuff like that. So a quick illustrative example. So suppose I have some underlying function that I'm trying to numerically take the derivative of, and I have these two sample points that I'm trying to look at. Now, without cheating and looking at the code block to figure out exactly how I got those points, there are an infinite number of different curves that would perfectly run through those points. Hi, this isn't a great time. Come on. One sec. Come on. Right, 2 points. So you can see I have a line that goes through them perfectly, a parabola. But if I want to know from these guesses at the curves what the actual slope for my underlying function at this point is, these two curves don't even agree on if it should be a positive or a negative number. However, if I go and sample my space a lot more finely, it becomes a lot more apparent what the actual shape is, and we can see that the slope here is actually supposed to be 0. However, this comes at a cost. Because remember, if you double the amount of sampling points you have in a single direction, but you do that in all 3 directions, we need to take the cube of that. So we'll actually be looking at 8 times as many points in our grids. So then at every time step, we're going to have to run over 8 times more cells, do 8 times more calculations to get to the next time step. But more than that, there are constraints on how big a time step you can take that depend on the size of your grid. So if we half the resolution of our grid, double the number of points, we'll also need to cut the time step in half as well, take twice as many time steps to get to the final time that we're aiming for. So in all, we multiplied a single number by 2 in our grid setup and multiplied the runtime of our calculation by about 16. So it's important to find a balance there. You need enough points to be able to accurately resolve the features you care about, but not so many that your simulation takes longer than the maximum wall time on the queue, for example. Um, so we're going to also look at a way that we can thread that needle in a couple minutes by having a different size grid in different places depending on what's going on where. Um, okay, so we will go back to the other window. Okay, so this is the same interactive job that we set up before for the last example, and then we're just going to toss out the old example. Right, saving. So in the data that I included for this workshop, I do have saved files of the simulation at different steps through it. So I have one that's just the geometry, one with the mesh, and then one that's the final the solved state for each example that I do. So we're going to use Fluent again. This time we're going to do a two-dimensional simulation instead of three-dimensional. So we're going to open up the Properties tab here. Okay. Geometry properties. And we're going to switch the analysis type to 2D. Okay, and then we're going to open up the geometry program. So this example is going to be fluid flowing over a cylinder. So to do that, we're going to first need not just the cylinder, which in 2 dimensions is just going to be a circle, but we're also going to need a rectangle that is the extent of our computational domain. Okay, so we're just going to work entirely in the XY plane. We're going to look at a couple more features in the sketching toolbox. We can turn on the grid to make it a little bit easier to estimate our rectangle coming up shortly. Show in 2D. Okay. And then we're going to draw a rectangle. And then we're going to add dimensions, and we're going to do it with a little bit extra steps just to make sure we're sort of centered on the origin. So we're going to add a vertical dimension. So I clicked on the top here, the axis here, and then once more to give it sort of where is it going to put the visual indicator here. And I'm going to set this to 7.5. Repeat that. And again, 7.5. So that's 15 meters. And then we're going to do the horizontal as well. So we're going to do 16 and 16 for 32 meters total in that direction. Again, I clicked on the edge and then the axis. Okay, and then we will also put a 1 meter cylinder in the middle. So we're going to use the circle tool again, draw, and then we will add a diameter to it. And we will set that to 1 meter. So in the concept menu, we'll click on surface from sketches. So this created a new sketch 1. Okay, sketch 1 in the XY plane and apply. And then we can generate our surface. And then this created a new body. And we will set this to be a fluid since this portion that's colored in here, that's going to be the fluid and it's going to be flowing this way through the rectangle and getting perturbed by the cylinder here. And then we make sure that the thickness here is set to 0. So we can close out of this. And then we can move on to meshing. Okay, yeah. So we will insert a method again. We will assign it the geometry here of our fluid. And we will change this to triangles. So that's sort of the equivalent of the tetrahedrons that we used before, but in 2D this time. So a triangle is the polygon with the fewest number of sides, and a tetrahedron is the polyhedron with the fewest number of faces. So they'll accomplish pretty much the same purpose here. We will also add, yeah. Let's see what this gives us at first. Yeah, so we can see that what it's automatically trying to do is give us smaller triangles near the cylinder here, and larger ones towards the edge, because the cylinder is going to be perturbing our fluid flow, and creating effects that exist on a smaller scale than they would in the bulk of the fluid. So that lets us sort of combine the benefits of small grids and large grids. Um, so we have the resolution to try and capture finer features where they'll show up, but we can also save on the computation power when we're computing things that we're pretty sure are going to be much more straightforward. But that's not exactly all we're going to do here, um, because that's actually not quite as small as we want those triangles to be. So we're going to add some inflation to the boundary. So we're going to tell it to make things even smaller, closer to the cylinder. So we're going to select our cylinder. There we go. We apply this to the, okay, the geometry is the fluid. There we go. And then the boundary is the cylinder. We'll use the first layer thickness method. First layer height to that. With 40 layers and a growth rate of 2.5. And then, yeah, we'll also change the mesh overall, decrease the element size to 0.025 as well. And then we can see that when we hit generate now, we will get finer polygons. whenever it finishes. Okay, well, I'm not entirely sure why it's okay. So I'm going to go to the backup.
Wh-
No, there. Okay, uh, there it goes. But you can see that we get a much finer mesh in here. Um, okay, double check and see if it actually did what I want before I actually go throwing this out to go to the backup. Okay, that's what I did wrong. That's set by that way too fine. Okay, that's how that's supposed to go. Okay, so we'll create the named selections again. So this will be our inlet. The outlet. And then control clicking on both of these, we can set them to be both the same wall selection. And we can call this the cylinder. And update. And then once this completes, we'll be back to the setup and solving stage again. Well, that's hanging too. I am going to go to the backup. Oh, well, okay. My interactive session is gone. That's probably part of the problem there. Okay. Okay. Sorry about that. And once this finishes, we'll once again be changing the model to laminar. At the air to just one in both of these fields. We change the inlet and outlet boundary conditions to 80 meters per second this time, so going much faster. So we'll see some interesting effects going on around the cylinder as it gets hit with that much wind. The outlet will just be yeah, we leave that as is. In reference values, we set to compute from inlet in methods. Change this from a so we set the transient formulation to second order implicit. And initialize. We just use the hybrid this time. So the interesting thing here is in calculation activities, we set this from 5. The default is 0. So this will save every 5th frame as we step forward in time so that we can look at them later. And then we run the calculation and we set things, we go for 50 iterations max, 20 iterations per time step, and a time step of 0.01. And then we click on calculate. So I have longer to talk about residuals this time. So this is a measure of how badly we violate constraints at each iteration. So you'll see as we go through an iteration, they go down and they jump up again as we go to the next time step where they start going down again. So it's basically at each time step, it goes through a process of refining the results that we get to be more accurate. And then as soon as this finishes, we will go plot our results. So we'll click on symmetry 1. And then this is a plot of the contour plot of the velocity in the x direction. And then we can use the time step selector from this button here to look at different time steps. So this is the initial state here when things are just getting started. And then this is what it looks like at the end. And we can see as we look through, we get these wiggles in the flow coming off of the cylinder. That is called the von Karman effect. Okay, so that was what I have prepared. Are there any questions about this?
Hi, Irene. I have a question.
Yeah.
Not really about the simulation, but about the ANSYS package on the HPC cluster.
Mhm.
Like what license is it? Is it like academic license, professional license, or if you know of it?
I'm not actually sure. Guillermo, do you know?
I think it's the full version. Is the license comes from Stadler, so I am assuming that. Can you check there in the version that you have there? But as far as I know, is the professional version.
Okay.
So it's not the same that the students have. Is the same version that the university pays for the college. So they don't know. See,
It's not forthcoming in what I have here.
let me see.
But
How I can see that.
seems like it's probably the full version because I think a lot of the time the logo will say if it's anything besides that,
Yes,
and I don't see
exactly. So let me see.
anything to that effect.
Okay. Well, thank you.
On the
Anyway, I'll
version,
try to find out. I'll because I have to go now. Thank you very much for
Okay.
for the lessons.
But yeah, it looks like this is the full version.
All right. Thank you.
I don't. Why you use the 2022 instead of the 2024? Any reason particular? Because
I
I
think there's
see that
something
we
wrong with
have the
2024 right
2021.
now, and
Okay. So not for a
decided to
reason.
focus on getting material ready for this instead of.
Okay. Well, because I'm trying to see, to answer that. To see which version we get. But we installed the 2024. And
It's in the
desktop with GPU when you
yeah,
select
it's
that version.
like it's in the drop down menu, but it doesn't seem to work right when I was trying to use it.
Oh, okay. Okay.
With like an installation level issue.
Well, what happens is that for certain things, if I recall correctly from Nate, the point is that for certain things, Fluent works, but there are graphics user interface applications or sub-applications in the ANSYS package that doesn't support Red Hat 7. So that's the reason why, for some people, it's not a big issue because they just run the simulations command line. So they have prepared. They
Right.
do everything that you do, what you did today. They do it on their own computers because it's much faster. You interact quicker with the mouse, keyboards, whatever, and they transfer that to the cluster and they run it there.
Right.
At that moment, they don't care about the graphic user interface, and that's what I'm trying to launch right now the ANSYS 2024 to see what I get. But that's what I recall. Certain applications will not work. The interface, the graphic interface will not work, but everything else works. So, and for some people, what they really care is the simulation. So that's what I remember.
Okay. Hi, can you hear me?
I can hear you.
Yes.
Yeah, I have just a simple question. So I'm not aware of this ANSYS package. It is something like a MATLAB program software or?
Kind of. It's very specialized in specifically these sorts of engineering physics simulations.
Okay.
But it
So,
comes with a GUI that's somewhat similar to MATLAB.
oh yeah, that's why I just felt like maybe it's something like a MATLAB software. So what kind of problem can this be used to? Is it basically like engineering, or can it also be used for like other research problems, for example, like physics? Or because I am from like physics background, so I was wondering like if this can be used in like physics research problems.
I would say yes. If you look at the toolbox here,
Yeah.
there's a lot of different components that you can use in ANSYS, and some of them do look like they veer more towards like magnetostatics. Sounds a lot more like physics than engineering.
Yeah.
Yeah, I will add to what Irene says, that it all depends to the physical scale you're working. So in this case, as far as I know, Fluent. So ANSYS offers a set of packages, and Fluent is just for the simulation of the fluid dynamics. They have other packages, for example, if you are adding chemistry to that. So if you are in solving problems in combustion, that is a different goal, because you have the fluid, but the fluid interacts, they make chemical reactions and they produce other fluids, another substance. That's another package that is called Forte, and it's also part of ANSYS. But still, you are dealing with the matter on a certain microscopic level. If you move into a, let's say, micro nano scale, and you want to really deal with the atoms, so the particles as such, I think this software is not for that level of theory, let's say. And there are some other packages, for example, that I know, for example, LAMPS, which is more for the micro, almost nano scale. So you
Okay.
still describe particles. You're still describing particles, classical particles. So basically balls that interacts with the Newton equations, that sort of thing. And at that moment, what you provide are force fields to describe the interaction of those particles. That's another
okay.
level of description. And this Fluent is not working, is not working at that level of description. And if you want to go down beyond that, so you're really sub-nano scale, so where you are really dealing with atoms, it all depends the kind of atoms that you are dealing with. So if you are talking about biological entities like layers and transferring protons across a protein or something like that, there are other packages that deal with that. So they are able to describe the atoms, they to certain level describe the hydrogens or the protons at that for that. Amber is one of those that I know that is specialized for biochemistry simulation. So that is also, you have the tubes there, but those are a different description. And if you want to go down beyond that, you need to now describe the electronic structure, and that's another thing. So that is an entirely different. So in summary, it all depends to the level of to the scale that you are working.
Okay.
And
Okay.
this Fluent is what you say is more engineering kind of thing. Is because
Okay.
dealing with the matter at a more macroscopic level. It could be micro tubes, but you cannot go beyond that. Let's say it still is dealing with those objects like a continuous matter, rather than describing the atomic or kind of aggregated kind of matter. So
Okay.
that's the idea. That's why we say it's an engineering code.
Okay. Okay. Thank you. Thank you
Yeah.
so much. Yeah.
And let me see. I actually tried to. I got it. To see if I get Fluent working. I'm trying to see to answer the question about the
Right, 24.
what is not here. To see what I see on the first screen. Well,